All right, everybody. Today we are talking about section 3.1. And I meant to mention that this last time at the end of last section, but the beginning of this section works just about as well. This is the cutoff point for the first exam, right? So section 3.1 is going to be the first section that shows up on the second exam. So if you are looking back over these mini lectures for the purposes of studying for the exam, for the first exam, then you'll want to go back to the ones before this. This section is not on the first exam. So with that being said, this section is all about the definition of the derivative. And for starters, we're talking about the derivative at a point. So we're gonna, next section, talk about the derivative as a function, but for now, we're gonna talk about the derivative, which is what that prime indicates, of a function at a particular point A. Right, so this is the derivative, right, that's what the prime symbol means, of the function f, and that's what f stands for, at a. Right, so for this purposes, we're talking about derivatives at an individual point. Right, if you've seen derivatives before, you more often see them talked about as a function, and then once you get it as a function, if you want it as a point, you plug it in. Right, a lot of our rules that are going to make taking the derivative a lot easier work that way. But similar to the way we started with that formal definition of a limit and worked our way up to the rules, we're going to do that same thing for derivative. So the derivative of f at a is the limit as x goes towards a of something that y'all have probably seen before in pre-calculus, the difference quotient. Right, so f of x minus f of a all over x minus a, and the order there doesn't really matter as long as you do it both the same way on top and bottom, right? You can have f of a minus f of x all over a minus x if that makes you happy, as long as the x and the a are in the same order on the top and the bottom. And we actually have two different versions of this definition, right? The second version says that we're going to have something called h going to 0, and we're going to have f of a plus h over f of a all over h. Right, and so these two are really the same thing with the transformation that x minus a equals h. Right, because if x minus a equals h, then x equals a plus h, a still equals a, and the limit as x goes to a of h equals the limit as x goes to a of x minus a, which we can just do substitution here and get that 0. That's why we said that the limit as h goes to 0. Right, so those are really just the same thing with that pretty simple transformation put in there. And when you're using this to find the derivative, because we're going to use something, because whenever we're using the definition of the derivative, we use one of these two things, right? And you can use either of them. This one is a little bit clearer where it comes from, right? Because this is delta f over delta x pretty directly. This one's a lot more useful later. Right? It's perfectly usable now, But come next section, we're going to have to use that one mostly to avoid some confusion. But we'll talk about that when we get to it. So a lot of this stuff in the section is hearkening back to what we talked about in that very first section. Right, so the slope of the tangent line at the point A, f of A is f prime of A, right? That's part of our definition of the instantaneous rate of change that we talked about in that very first section. And so the equation of the tangent line is y minus the y-coordinate of the point we know equals m, which is the slope, times x minus the x-coordinate that we know. Right? So that's just the point slope formula for a line, because the tangent line always goes through that point, and we learn in this section that its slope is this guy. So we also learned some preliminary rules, and that is that if f of x equals mx plus b, then f prime of a equals m, no matter what a is. So for all a. And similarly, if f of x equals b, so just a constant, then f prime of a equals 0 for all a. And really, this is just a rule and then a very specific instance of it, right? Because we can think about b as being 0 times x plus b, so m is 0 in this particular case. So, we've got those preliminary rules. We are going to, for starters, do this the long way and see if we can check, right? So first off, we'll go up here and then we'll duck back down. So problem 1, use the definition to find f prime of 3 when f of x equals 3 minus 5x. Now, we can make a note to ourselves. Our rules say that the answer equals negative 5, right? That's the m from up here, right? If we compare this guy to this guy, m is negative 5 and b is 3. So according to this rule we have right here, the derivative at 3 should be negative 5 because the derivative at any point should be negative 5, right? But this problem specifically says use the definition, so we can't just use our rules, we have to use our definition, right? And in this case, it's going to give us a chance to practice in a scenario where we know what the answer should be already. Right, our first definition was that f prime of a equals the limit as x goes to a of f of x minus f of a all over x minus a. Right, so we have our f of x, and this part right here tells us what a should be. So if we want to find f prime of 3, then that should be the limit as x, because that's always going to be our variable, goes to 3 of f of x minus f of 3 all over x minus 3. So now we can fill that in a little bit. F of x, our problem tells us, is 3 minus 5x. And that means that f of 3 is going to be 3 minus 5 times 3, right, where this 3 comes from that 3, right, all over x minus 3. So let's simplify a little bit, distribute that negative through to get minus 3 plus 15 all over x minus 3. 3 and negative 3 are going to cancel each other out. So we get minus 5x plus 15 over x minus 3. Now, whoops, I've been doing a bad here because there's supposed to be a limit on all of these guys. Right, and so here would come the point where maybe I try substitution. Right, but when I do that, I get negative 5 times 3 plus 15 all over 3 minus 3. That's 0 over 0. And that means we're not done, but it is an indeterminate form like we talked about last chapter. And with indeterminate forms, we've got some tricks we can do. Right, and the first one is to factor and cancel. So the stuff on the bottom is about as factored as it's possible for a polynomial to be. So that just leaves me the stuff up top. And I notice that I can take a 5 out, but I also notice that I'd kind of like these x's to match up. So I'm actually going to take a negative 5 out because of that negative there. So that means we just get an x here and a minus 3 here because I want these negatives to cancel out to give me that positive. And then I can cancel and figure out that what I'm really looking at is the limit as x goes to 3 of negative 5. And that is, in fact, as we were expecting, negative 5. Right? So we took a lot of time to get to the place where we knew where we were going, but that means that we were able to check ourselves and determine that we did probably do it right. Because we got the answer we were expecting. Right? Let's see. So next up, let's find the tangent line at 1 for f of x equals x squared minus 7. Right, so when we have a problem like this, we want to find the tangent line, right? That's the main instructions. We need to remember what formulas do we have for the tangent line, right? So we recall that our formula for the tangent line was y minus f of a equals f prime of a times x minus a, right? And so the key thing about what we have here, the key thing we're missing is what a is, right? But whenever you see at a number, that's telling you what a is for all these values. So this tells us that a equals 1, right? So that means that we need to know what f of 1 is, and thankfully that's pretty easy, right? We get 1 squared minus 7, so negative 6. And we also need to know what f prime of 1 is, right? That's probably going to be the harder part. So we go to our definition, and just for fun this time, let's use the second definition, right? So let's use the limit as h goes to 0 of f of 1 plus h, right? It's usually f of a plus h, but for this problem, we know that a is equal to 1 minus f of a all over h. Right? So we can plug all that in. Right, so that's 1 plus h squared minus 7. And luckily for us, we've already figured out what f of 1 is. So we're going to be subtracting f of 1 all over h. Right, so we've got the limit as h goes to 0 of 1 plus 2h plus h squared. When we multiply this guy out, right, we have a rule for that. And we can also use FOIL if we want to, because 1 plus h squared is just 1 plus h times 1 plus h. And then we're going to subtract 7, and we're going to add 6, because these two negatives cancel each other out. Right, now 1 minus 7 plus 6 cancels out. We get the limit as h goes to 0 of 2h plus h squared all over h. Now, we could do substitution here and go ahead and plug 0 in, but I don't really need to look at that. I don't really need to do that. I can just look at it and see that's going to be 0 over 0. So I'm going to go ahead and try to factor out stuff before we do the substitution step. And I notice that I can factor out an h from up top, which is exactly what we have down below. And I get that this is the limit as h goes to 0 of 2 plus h, which now when I do substitution just gets me 2. Right? So we have there f prime of 1. Right? So to finish out the problem, our tangent line is going to be y minus f of a, right, which we figured out up here is negative 6, equals f prime of a, which we just figured out is 2, times x minus a, which we said was 1. Right, and then we can simplify this a little bit if we want. Right, we can even put it in slope-intercept form, right? And how you leave it depends on what the instructions are, right? If the instructions don't say, it doesn't really matter, right? If the instructions say put it in slope-intercept form, then you want to get it to here. If the instructions say point-slope form, you can get it to there or there. Either one of those are in point-slope form. Really, I guess this one is the more in point-slope form. But that's one of the cases where you'll need to read what the problem instructions say. This one doesn't give a specific form of it, so you could do either. Right? And one thing to keep in mind, I didn't choose this method instead of this method because of the problem I was doing. I only chose the different one so that y'all could see an example of each type. Which version you use, which formula you use for this section is entirely up to you. Whichever one seems like it'll be easier for you to work out, that's the one that you should do. So we're going to do one more. So we're going to find the derivative at 5 of the function square root of 14 minus x. Right? So for this one, I'm going to go back to that first definition that we used. So the limit as x goes to 5, right, because that's what's inside the parentheses here, of the function minus the function with 5 plugged in, right, all over x minus 5. Right, we probably want to simplify this a little bit up top. and be happy that it's going to simplify even more. All right, so we get limit x goes to 5, the square root of 14 minus x minus 3 all over x minus 5. Now, if I do substitution, right, I'm going to get square root of 9 minus 3 all over, oops, got too many 3's in there, 5 minus 5, which gets me 0 over 0. Right, so one of the things about this process is that if you are finding the definition using, or the derivative using this limit definition, this is an entirely extraneous step, because so long as you plug things in properly, it will always be 0 over 0. So I guess it's not really extraneous, it's just a checking yourself step. If you haven't canceled anything out yet, your substitution step will always give you 0 over 0 if you did the first part right. Right? So if you're confident that you plug things in correctly, you can skip the substitution step and go ahead and try to factor and cancel. Right? But regardless of whether we chose to or not, or we did choose to in this case, we're going to need to do that factoring and canceling. Right? So this is a problem like we had in section, what was it? 2.5, where we came up with the rule factor and cancel. But it's that special kind of weird factoring where we have that square root involved, which makes it difficult to factor in general, which means that first we're going to kind of have to unfactor it, and then we're going to simplify. Right? And if we recall, we do that by multiplying top and bottom by the conjugate. So we've got this guy here, and we're going to multiply by the numerator, but the conjugate of the numerator. Right? Which means instead of this subtraction, we're going to have an addition, and otherwise it's going to look exactly the same. Right? And if we multiply by the same thing, top and bottom, we're not actually changing anything. And it's a really easy multiplication up top, and we don't actually want to do the multiplication down bottom. We're just going to leave it the way it looks. Right? Because that's technically factored, so we don't want to unfactor that part. That wasn't the part that was giving us trouble. Right? But the reason we multiply by the conjugate is that means it gives us the first thing squared, which the square root of 14 minus x squared is 14 minus x, minus the second thing squared. Right? That's a really weird 3, but I promise that's a 3. So we get the limit x going to 5 of 5 minus x, since 3 squared is 9, x minus 5, square root of 14 minus x, minus, plus rather, 3. Right, now these guys almost cancel, but I'm going to do one simplification thing. To make them really cancel, we need to pull out a -1. Right, and that makes them look exactly alike, because pulling out a -1 swaps the order of subtraction. Right, so now these guys cancel, and we're looking at the limit as x goes to 5 of -1 over the square root of 14 minus x plus 3. So now we can try substituting, and we get the square root of 14 minus 5 plus 3. It's -1 over the square root of 9 plus 3. So that's -1 over 6. And so this is, just to remind ourselves, the derivative at 5. So the key thing with these types of problems means identifying what A is, and making sure you follow the directions of the problem, right? If it says you need to use the limit definition, then you can choose which one you want to use, but you got to use one of them. One thing along those lines to pay attention to, I don't recall, but sometimes MyOpenMath specifically will tell you to use a particular one of the definitions, just because that helps it understand the input better, so it can be so there's only one answer that it's looking for as opposed to things that look very closely similar. I don't remember if there are any problems where it makes a difference, but do be sure to read the directions and make sure if it says to use the version with H, use the version with H. If it says to use the version with X minus A, use the version with X minus A, right? But that just comes down to a good rule of thumb, which is always read the directions and make sure you follow it up. Okay. So next section, we're going to be talking about the derivative as a function. So we're going to find f prime of x, right? We've just been able to find f prime of numbers so far, but we're going to try to find f prime of a variable. And that's also the section where we get a whole bunch of rules. So instead of having to use this limit definition, we're going to be able to use those rules. So I will see y'all to talk about that next time.